Okay, today we're going to look at products. All right, and a product is the term or is an outcome when we multiply two terms together. All right, so it's the outcome of a multiplication. So if we had 2 times 3, which would be 6, we call this answer the product of 2 and 6. And I think you know this because you have been doing this or familiar with these terms from previous years of you math. When we have 2 divided by 3, this outcome, which is equal to 2 over 3, we could say that, or 0.67, is referred to as the quotient. All right, it's the outcome of a division. If we had 2 plus 3, okay, which is equal to 5, this is referred to as the sum. Okay, remember when you were in primary school and the teachers were like, do your sums or do your math sums, and 2 minus 3, we refer to this as, which is a -1, as the difference. And we've seen the sum and difference before, like when we are looking at how to factorize, which will be our next section. Here, in order to factorize this, we would factorize this into x plus y and x minus y, and we call this the sum and the difference of two squares. Okay, so when we look at products, or if we look at a term, such something like 2xy, here we know that that's a 2, but these and the x's and y's are our unknowns. Okay, we don't know what value they are just as yet. So we are representing them with a letter of the alphabet, and we are going to treat them, even though they are unknowns, we're going to treat them as if they exist. All right. And as long as we treat them in a way that is in accordance with mathematics and rules of algebra or whatever section we might have unknowns in, we should be able to solve for them. Okay, and find out what their value is. That is the purpose of using maths. Okay. These unknowns are also called variables. So variables means that they are allowed to vary. Vary meaning that their values can change. Okay. But this term, we call this in maths, we call this a term. And a term is a mathematical object. It's like an object, like a cup or a saucer or a pen. All right, it's almost like a mathematical noun, something that we can feel or see or touch. Okay. And oh yes, the other thing that we need to understand, even though we write it as 2xy, what we actually have here is 2 times x times y. Okay, so 2xy, 2x and y are individual factors that make up this term. If we want now to, let's say x and y represent something, x could represent, be a variable for the number of hours in a day, and y could represent the number of meals you eat in a day. If we now add 5 to our expression, so add 5 to our mathematical object, our term, that we call an expression, an algebraic expression, because this is the section under algebra, okay? And it's like an expression. It's like, your emojis that you use to signify how you're feeling, all about expressions. If you think about it like an expression, or like I'm happy or I'm sad, or as a measure of you expressing your feelings, okay, then we can see that this expression holds some content, and it holds a sort of the equivalent would be mathematical content, but some sort of expression in your daily lives. Okay, so this is like almost a sentence. It's like saying, oh, the boy kicked the ball. All right. So what an algebraic expression is it consists of terms linked together by mathematical operations. And you know these operations, we just went through them. Sum, difference, product, quotient. Okay. And here we refer to the 5 as being our constant term, because we know the value of this term is equal to 5. And whatever 2x and y is, we're going to add 5 to it, no matter what x and y is, no matter how many meals you eat in the day, no matter how many hours there are in a day, whatever that is, we're going to multiply it by 2, and we're going to add 5 to it. And so the 5 we refer to as a constant. Constant, okay. Now, this term, or this expression, sorry, is made up of 2 terms. Made up of 2 terms. And when we have 2 terms, we call that a bi, meaning 2, and nomial, referring to terms. Okay, nomial. When we have 1, like an x or 2xy, we call that a monomial. Mono meaning 1. Monomial. Okay. You'll see these terms also in biology, those of you who do biology. And when we have 3 terms, which we are going to look at very extensively, or which we do look very extensively at high school mathematics, we refer to this as a trinomial. Trinomial. Okay, and when we have more than 3 terms, we generally refer to that as a polynomial. So tri meaning 3, like a triangle, the number of sides in a in that shape. Or when we have more than 3 terms, we're going to refer to this as a poly, meaning many nomial. Okay. So one of the very first things that we have to learn how to do, and this section will follow from the real numbers section, is we're going to need to learn how to multiply terms. Multiply monomials by binomials, binomials by trinomials. And one of the techniques that allows us to do this efficiently and result in an outcome is a law known as the distributive law. So there's an idea of distribution here, and distribution just means spreading out, or it has an idea of logistics by it. Like when you order stuff online and the logistics company delivers to you, they distribute it to you. Or like when we were going through COVID and everybody needed to get their vaccine, those vaccines were distributed throughout the world. So the distributive law is very much like that. It has that same idea. And the law simply states that if we have a monomial multiplied into, let's say for this example, a binomial, what we do is we multiply each of the terms by this monomial. All right, so we're going to have A times B plus A times C. And we're just going to simply write this as AB plus AC. Okay, and we also have to pay attention to the signs that we have here. So this operation of the binomial, which is an addition, is also kept true in the outcome. So we can't have a minus here, but you will get minuses sometimes. If we have A into B minus C, here we're going to have AB minus AC. Now remember, we don't have to put the dots in all the time. We can just appreciate that these are just single terms. Now, if I had A negative A minus B minus C, and when I distributed this, like I'm going to do now, we have to be careful because here the B is positive, but the C is negative. So when we multiply negative A into positive B, we're going to have negative AB. But when we multiply negative A into negative C, we're going to get a positive outcome because a negative times a negative is a positive. So we have to be ultra sensitive to the signs, but that's true for all math. So that shouldn't be any news to you. Okay. So let's test if this distributive law works. Okay, so if I had 2 into 2 plus 3 plus 4, okay, usually in math, what we would do is we'd go, well, this is 2 times, and here we have brackets, so we got to focus on these brackets first, right? Because those are the rules. We have to remember the BODMAS rule, right? Which you probably know about. Okay, so here we have to focus on the brackets first, but we will talk about that a little bit later. We would have to first find the sum of these 3 terms or numbers, which is 2 plus 3, which is 5, plus 4, which is 9, and then we can multiply our 2 by 9, and that equals to 18. Now let's apply the distributive law to this question and see if we end up with 18. So let's distribute or hand out this 2. Okay, distribution is like distributing pamphlets at the robots. Okay, we're distributing a pamphlet of this 2 to all of these 3 terms in here. So we're going to multiply 2 by 2 first, and then we're going to add, because here's an addition of positive 2 times positive 3, which is 2 times 3. And then we're going to do the same thing for this positive 4. Positive 2 times positive 4. Okay, now let's add all of these up. 2 times 2 is 4. 2 times 3 is 6. And 2 plus 4 is, 2 times 4 is 8. This is 2 times 3, yes. So now we can add up. 4 plus 6 is 10 plus 8. And you can see that we arrive at our original answer that we had when we didn't use the distributive law. Okay, so what the distributive law allows us to do now is work with unknowns and variables and gives us a technique of applying mathematical rules in terms of products and unknowns so that we can still use mathematical laws and still preserve the initial almost requirements of what these variables signify without changing it. Okay, so whatever they signify in the real world, like for example, we said that this was the length of day and that this was the amount of meals you eat in a day, we can still keep them in that form and use the distributive law in such a way that we do not allow any breakdown of what these represent. They're preserved, they're mathematically preserved, if that makes sense. Okay, I might be over-explaining things a little bit, but you will see very soon how we will use algebra answering word problems, and we are going to have to take word problems, which is in the language of English, or whatever language that you speak, and we're going to now translate that into a mathematical language in order to solve our problems. Okay, so again, if we use the distributive law here, we have 2x plus 2y. And here, these are unlike terms. We cannot simplify them further. So what is a like term and what is an unlike term? So a like term is when we have when we have variables, when both of our variables are the same and their exponents are the same. Here, do we have the same variable? No, we have x and a y. Are their exponents the same? Yes, they are. But as long as their variables are different, we cannot add them. So 2x plus 2y will remain 2x plus 2y. But if if this was our question, and here we use the distributive law, we would end up with 2x plus 6x. Now, here we would end up with like terms. Why are they like? They are like because we have the same variable, x and x, and they both have the same exponents. So here, this answer is 8x. Okay, so if we had, let's do another question here. Let's modify this a little bit. If we had x plus 3x squared, and we use the distributive law again, we would end up with 2x plus 6x squared. All right, now I have the same variable, but our exponents are not the same. So therefore, again, this is unlike and remains as 2x plus 6x squared. Okay, so we're going to have to scan after we do our multiplication using the distributive law. We're going to have to scan for like terms to see if we have like terms. And if we have like terms, then we can simplify them by adding or subtracting them. Okay, so the first thing that we're going to be looking at is how to multiply a monomial into other forms, either a binomial, a trinomial, or a polynomial. That's the first thing. You will remember that if we had an x into a y, that here we have two monomials, we'll just multiply this as x times y and end up with xy. Okay, but if we start going through the questions on section A, question number 1 is 3x into 6n minus 7. Here we have a monomial with a negative sign, which we have to be very careful with, being multiplied into a binomial. So let's apply the distributive law. So the first step is to take negative 3x and multiply it by 6n. And then here we got to watch out because we've got a negative term times a negative term, and it's going to become a positive. Okay, so we're going to have 3x times 7. Okay, but I'm going to write this like this so that you see that. I'm going to have a negative, let's do it like this so you see that. Okay, a negative 3x times a negative 7. And so what would this equal? So here we can multiply these two terms. That's equal to negative 18. X times n is the same as x times y. So here we would have xn. And here what's going to happen is this is going to become a positive. We are going to multiply those two numbers, and that's going to become 21. And here, all that's going to remain is the x. So this is our answer for our first question. So we have to be careful of our negatives. Now, I'm not going to write this step out. I have included it in the work solutions, but we are going to work through these questions and apply the distributive law. Okay, this is an essential technique that you have to master in the early stages of grade 10, and you have been introduced to this in grade 9, I think, and in grade 8, you would have done this, a little bit of this as well. So we have to make sure that this is sorted. Otherwise, if this, remember, grade 10 is the foundation here. We are building a foundation for our house. We are planting a seed, and we have to make sure that when that seed sprouts, that root system is strong, so that when we go into grade 11 and 12, and the plant is growing and the house is getting built, that it is built on solid ground. Okay, because that's where most of the issues come with math, is that foundations are not strong enough. Let's look at question number 2. Okay, so here we have, I don't know why my pen is making this so thick, but we're going to have to just deal with this today. Negative 4. I think I put in a lot of negatives in here for you to get practice with. 4a squared b to the 8 into 8a. 8a. Okay, let's write that again because that doesn't look very neat. 8a b to the 5 minus 7a to the 4 minus 9b squared, 9b squared. Okay, let's multiply. First step, oh, and by the way, we have a trinomial multiplied by a binomial. Okay, so the first thing we're going to do is multiply that negative 4 by that 8, and we're going to end up with negative 32. Then, this section of work expects you to know your exponent laws. And the exponent law that we're going to use here is the very first exponent law that you guys study and learn, and that is a to the m times a to the n is equal to a to the m plus n. So what that means is that if we have two terms with the same basis, we can add their exponents. All right. So here, in order to use that law and carry out this product of this operation, or carry out this process of multiplication or finding products, here we're going to get a into 2 plus 1. Do you see that? That exponent plus that exponent times b, but we're not going to write the times just to save time and to save space and to save this looking too outrageous. And that's going to be 8 plus 5. All right. So here that would become negative 32, a to the 3, b to the 13. Okay, let's do the next one. So negative 4 times negative 7 is positive 28. Here there's no b exponent, but I have an a to the 2 plus a to the 4, which times a to the 4, which means when we add the exponents, it's going to be a to the 6. And when we multiply the b to the 8, there are no other b's there. So this is just going to be b to the 8. And let's multiply the last one. Again, a negative times a negative is a positive. 4 times 9 is 36. Here I have no a, so this is a squared, but I do have a b. And remember, this is a b to the 8 and a b to the 2. We can add the exponents, which is b to the 10. So here, this is our example. Sorry, this is our answer. B to the 8 plus 36, a to the 2, b to the 10. All right, now we have to scan to see if we have like terms. And it appears that we don't, because our exponents, even though we have all a's and all b's, which are the same, our exponents are different. Here we have a 3, here we have a 6, and here we have a 2. So we can't add these. All right, they are unlike terms. We don't even have to look at the b's because we can already see the a's are not like. And so then this becomes our answer for question 2. All right, so we're going to continue doing these and getting used to how this works. Number 3 is a little bit of a tricky question, because now what we are doing is we are adding a layer or another layer, and we're bringing in another section of maths, namely fractions. So we have 1/3 over 1/3 a cubed multiplied into 6a to the 5 times 18a squared b to the 3 minus 9a to the 3 b to the 5. Okay. So here we're going to multiply 1/3 by 6, and that's going to leave us with 6 over 3, right? Remember, fractions multiplied by 6 is the same as 6 over 1, so this becomes 6 over 3. And here we have the same base, so we can add exponents. So that becomes a to the 8. Here we're going to have 18 over 3. And we're going to add exponents of a, which is going to be 3 plus 2, which is a to the 5. There is no b's, so that will stay b to the 3, minus 9 over 3. And here we're going to have a to the 6. 3 plus 3 is 6. Remember, you add. Okay, we're multiplying. Some students will say, oh, this is a to the 9. No, we add exponents. We don't multiply exponents. So this is a mixture of it's a tricky big thing because we're multiplying and then we have to remember that we have to actually add the exponents even though we're multiplying. And then we also got to take into account that there are different signs that we're going to watch out for. And then we also have fractions. And then after that, we got to see whether we have like terms. So it's a lot of processing power that our brains require in order to do these questions. So the best thing is to take it slow. And here we're going to have a b to the 5. Okay, now we can simplify all of these because all of these numbers are divisible by 3. 6 divided by 3, or 6 over 3 is 2. That stays a to the 8. 18 divided by 3 is 6. That's a to the 5, b to the 3. And 9 divided by 3 is 3. So that stays a negative because we are multiplying it by a positive. 5. And can we simplify this further? No, because there's an a to the 8, a to the 5, and an a to the 6. So even though our bases are the same, they have different exponents. And so that's our answer for question number 3. Question number 4 is slightly more simple, but with question 4, we have a lot of different variables. Okay, so this is 3t to the 5 into 4abx. We got 3 unknowns in a row. Plus 5tab. So here we have 1, 2, 3, 4 different exponents. Now, in reality, or if whatever this expression mimics or models in real life, you will see that there's a lot of different things going on here. Okay, this is a complex situation. So by using the distributive law, it still allows us to handle this complex, all these things that these variables represent, but we can still multiply it by 3t to the 5 and still ensure that we haven't changed the values or misrepresented what these values or these variables stand for. Okay, so 3 times 4 is 12. Here, there's no t. So here, this is just abx t to the 5. Looks terrible, but hey, we are doing some pretty impressive things here with our distributive law, and we are still finding answers. 3 times 5 is 15. Now here I do have a t, and this is t to the 1 plus t to the 5, so that's t to the 6 ab. And that is our answer for question number 4. And you can see that they are all different unlike terms. Question 5, we revisit fractions. So this is 3 over 2, just a fraction, into a trinomial of 3p to the 6 minus 5 over 8. Now here I also put a fraction in the question, or in our trinomial, into 3.5. Ooh, looks crazy, but remember, you can use your calculator here. But I'm not going to use a calculator because I want us to do revision on how to do fractions properly because it's essential. 3 over 2 times 3, remember this is 3 over 1, would be 9 over 2. Okay, and there is no variable here, so that stays p to the 6. Let's multiply 3 over 2 times 5 over 8, which is equal to, now, multiplication of fractions, numerator over numerator, denominator over denominator. So this becomes 15 over 16. Okay, p. And this is a positive. That's just a 5 from that. Now, here, we're going to have to convert this mixed number to an improper fraction in order to multiply it out properly. All right, how do we do that? So if we have a mixed number, you can do this in a calculator, guys. I'm just doing it out so that just to refresh our memories on other sections of math, because we don't want to get too cozy using our calculators, because I find students do that a little too much. Anyway, so mixed number to improper fraction. We're going to multiply these two numbers, okay? The constant term by our denominator, which is 3 times 2, which is 6 plus 1, 7. So this is equal to 7 over 2. And then we add it to the numerator. So if we have A and B of C, to get into our improper fraction, it's A times C, A times C plus B added to B over C. Okay, let's just do another quick example. So we multiply A to C and then add it to B. So if we had a mixed number of 6 and 2 over 3, we're going to multiply these two numbers. That's going to give us 18 plus 2 is 20, and we keep the denominator, which is 20 over 3. Okay, this is just to refresh your memories. So here, this becomes 3 times 2. That, remember, is 6 plus 1 is 7 into 7 over 2. I'm actually going to write that over here now. So this is 7 over 2 instead of 3.5. And now we can multiply numerators by numerator and denominator by denominator. So here we're going to end up with, do it on the side. This is going to be 21 over 4. Okay. And now let's see if we can simplify all of this. It kind of looks like that's going to remain 9 over 2, 15 over 16. We can't really simplify that. And 21 over 4, 21 is 21 divisible by 4? I don't think so. It's 4, 8, 16, 20. Yeah, no. So this is our answer for question number 5. Okay, and do we have like terms? No, we have a trinomial with 2 of the same bases here, but remember these exponents are different, and here we don't even have an exponent. So these are all unlike terms. Let's look at question number 6, the last one. So here we have 2 over 9 into 3x squared minus 4x plus 32 over 33. Okay, let's distribute. So 2 times 3 is 6 over 9. And here we have an x squared. There is no variable here. Here, this becomes minus 8 over 9x. And this becomes 32 times 2 over 9. That is going to become, just hold on a second here. So this is going to become 64, and 32 times 2 is 64, and then 33 times 9 is 297. Okay, now here we can simplify that because 3 goes there 2 times and 3 goes there 3 times. So this is 2 over 3x squared, and 8 over 9 we can leave as 8 over 9, and 64 over 297 stays 64 over 297. You can put it in your calculator. You will see that it does not simplify. So these are just the questions that I set for you on distributive law. And remember to drive the message home, if we had A into B plus C plus D plus E plus F, now can you see if these 5 different variables represent something completely different and we needed to multiply all 5 of them by a certain other variable, okay, that's complex. It's 6. We are distributing 6 or 1 variable to 5 other variables. Those are 6 variables at play. It's a lot to handle, but using this law, it allows us to multiply all of these variables by one answer and saves us a lot of time. So here we have AB plus AC plus AD plus AE plus AF. And remember, all of these are unlike terms. We will look at in the next section, in section B, we are going to be dealing with like terms. And in that case, we are going to have to simplify.